Hello there, and welcome to Midnight Science, where curiosity slows down, the lights grow soft, and science takes the long, quiet road towards sleep. Tonight, we are going to talk about energy, a word that is everywhere. In physics, in biology, in chemistry, in engines, in stars, in storms, in food, in fire, in the beating of a heart, and also, unfortunately, in many places where it becomes stretched, softened, and turned into something it was never meant to be. People say energy when they mean mood. They say energy when they mean personality. They say energy when they mean atmosphere. They say energy when they mean hope, luck, intention, or some invisible emotional weather around a person. And in daily language, that can be harmless. We all understand what someone means when they say a room has a calm energy, or a person brings good energy. Language is flexible. It wanders. It wears strange hats. But physics is different. In physics, energy is not a vibe. It is not an aura. It is not a mystical glow around the body. It is not a cosmic reward system. It is not a secret force waiting for positive thoughts. And it is not the vague energy stuff that often floats around the edges of popular culture. In physics, energy is a measurable quantity. It can be calculated, transferred, stored, transformed, tracked. It can move from one system to another. It can appear as motion, heat, light, chemical structure, electrical potential, nuclear binding, gravitational position, elastic stretching, sound, radiation, but it does not appear from nowhere, and it does not simply vanish into nothing. That is where the first law of thermodynamics begins. The first law is sometimes written in a compact mathematical form. The change in internal energy of a system equals the heat added to the system minus the work done by the system. But before we enter the formula, we should stay with the idea. The universe keeps an account, a quiet account, not a moral account, not a spiritual account, a physical one. Energy can change costume, but it does not escape the ledger. A flame heats water. The water becomes steam. The steam pushes a piston. The piston turns a wheel. The wheel drives a machine. The machine produces motion, sound, friction, and heat. At every stage, energy is changing form. But the total accounting still matters. Something warms, something cools, something moves, something slows, something expands, something does work, something loses internal energy, something gains it. This is not poetry pretending to be science. This is the foundation of thermodynamics, and thermodynamics is one of the deepest and most practical branches of physics. It was born not from mystical speculation, but from engines, heat, pressure, steam, metal, labor, industry, and measurement. People wanted to understand why steam engines worked, how heat became motion, how much work could be extracted from burning fuel, why machines wasted energy as heat, why some processes could happen naturally and others could not. The first law emerged from the realization that heat and work are not unrelated things. They are both ways of transferring energy. Heat is energy transferred because of temperature difference. Work is energy transferred when a force acts through a distance, or when a system pushes, pulls, expands, compresses, lifts, turns, or moves something. Internal energy is the energy contained within a system, in the motion of molecules, in their interactions, in their vibrations, in their rotations, in their microscopic arrangements. So when we speak scientifically about energy, we are not talking about a mysterious personal field. We are talking about a quantity that appears in equations, experiments, engines, weather systems, living cells, and stars. This matters because the word energy has been borrowed so often that its scientific meaning can become blurred. And when a scientific word becomes blurred, it can start to sound deeper than it is, or softer than it is, or more convenient than it is. But real energy is not convenient. It follows rules. You cannot create energy by wanting it. You cannot erase energy by ignoring it. You cannot build a machine that produces endless work without fuel, input, or change somewhere else. You cannot get more energy out of a system than the accounting allows. The first law is one of the reasons perpetual motion machines of the first kind cannot work. A machine that creates energy from nothing is not just difficult, it violates the basic conservation of energy. And nature is not known for approving bad bookkeeping. The universe is patient, but it is a strict accountant. That is why this law is so powerful. It applies to a cup of tea cooling on a table, to the engine of a car, to the metabolism of a sleeping body, to the heat flow in Earth's atmosphere, to a refrigerator, to a power plant, to a volcano, to a star, to every physical system where energy is transferred or transformed. The first law does not say energy is always useful. That is a different question. Closer to the second law of thermodynamics, energy can be conserved while becoming less available for doing useful work. A hot engine releases waste heat. A moving object slows because friction turns organized motion into microscopic thermal motion. A battery drains as chemical energy becomes electrical work and heat. The total energy is still accounted for, but the quality and usefulness of that energy can change. This distinction is important. The first law is about conservation. The second law is about direction, entropy, and the limits of useful energy. Tonight, we begin with the first law, the quiet rule that says energy is not created or destroyed in an isolated system. It changes form. It crosses boundaries. It enters as heat. It leaves as work. It hides in microscopic motion. It shines as light. It flows through matter. It is stored in bonds. It moves through circuits. It warms planets. It powers cells. It does not need mysticism to be astonishing. It is already astonishing. Think of sunlight reaching Earth. Energy produced in the sun travels across space as electromagnetic radiation. Some of it warms the atmosphere, oceans, rocks, and living things. Some drives winds. Some evaporates water. Some becomes chemical energy through photosynthesis. Plants store it in molecules. Animals eat the plants. Cells break molecules apart. Muscles move. Bodies warm. Thoughts happen in brains powered by metabolism. Eventually, much of that energy is released as heat, radiated away into the cold surroundings of space. Not destroyed, transformed, passed along, counted. The path is vast, but the principle is the same. Energy moves through the world like a silent currency of change. But unlike money, it is not invented by belief. It is not improved by slogans. It is not multiplied by wishing. It belongs to physical systems. And to understand it, we need careful words. System, surroundings, heat, work, internal energy, conservation. These words may seem plain, but they are the doorway into one of the greatest ideas in science. The first law of thermodynamics tells us that every flame, every engine, every breath, every falling stone, every glowing star, and every cooling cup of coffee participates in the same deep accounting. Energy enters, energy leaves, energy changes form. But the total story must balance. This is the real science behind energy. Not energy as mood, not energy as magic. Not energy as a mysterious personal vibration. Energy as physics, energy as measurement, energy as transformation, energy as the quiet ledger of the universe. And in this video, we will follow that ledger slowly. From heat and work, to engines and fire, to the human body, to Earth's weather, to stars, and to the simple, powerful idea that when something changes, energy is always part of the story. So get comfortable. Let the room become still. Let the word energy lose its fog and return to its scientific shape. Tonight, we begin with the first law of thermodynamics, a law that does not shout, a law that does not sparkle, a law that simply keeps the books of reality. Energy is one of the most useful ideas in all of science. It is also one of the hardest to define in a simple sentence. We often say energy is the ability to do work. That definition is common and useful, but it is not the whole story. In physics, energy is a measurable quantity associated with the state of a system and its capacity to produce change. A moving object has energy. A stretched spring has energy. A hot cup of tea has energy. A battery has energy. A raised stone has energy. A beam of light has energy. A chemical bond stores energy. An atomic nucleus stores energy. A spinning turbine carries energy. A vibrating molecule carries energy. Energy appears in many forms, but it is not a substance you can pour from one jar to another. It is not a glowing fluid hidden inside matter. It is not a spiritual fuel. Energy is a way of describing what physical systems can do, how they can change, and how they can influence other systems. A stone held above the ground has gravitational potential energy. If you release it, it falls. As it falls, that potential energy is converted into kinetic energy. Kinetic energy is energy of motion. The stone speeds up. When it hits the ground, its organized motion does not simply disappear. Some energy becomes sound, some becomes heat, some goes into tiny deformations of the stone and ground. Some may create cracks or vibrations. The form changes. The accounting remains. This is the scientific beauty of energy. It lets us connect events that look different. A falling stone, a burning candle, a moving car, a cooling cup, a beating heart, a glowing star. Different systems, different scales, different materials, but the same principle of energy transformation runs underneath. Energy is the bookkeeping language of change. Now consider a hot cup of tea sitting on a table. It seems still, quiet, almost asleep. But inside it, molecules are moving. Water molecules vibrate, rotate, collide, and exchange energy. The hotter the tea is, the more microscopic energy is associated with that molecular motion. The tea transfers energy to the cooler air around it. It warms the cup. It warms the table slightly. It sends infrared radiation into the room. Slowly, the tea cools. Its internal energy decreases. The surroundings gain energy. No mysterious force is required. No hidden mood, just temperature difference, molecular motion, and heat. This is real energy, measurable, traceable, physical. Now, think of a battery connected to a small lamp. Inside the battery, chemical reactions can separate, charge, and create an electric potential difference. When the circuit is closed, electric current flows. Energy stored chemically in the battery is transferred through the circuit. The lamp emits light, it also warms up. The battery's chemical energy decreases. The room receives light and heat. Again, energy changes form. Chemical energy, electrical energy, radiant energy, thermal energy. Not magic, not a metaphor, a physical process. Now think of a stretched spring. When you pull a spring, you do work on it. You apply force through a distance. Energy is stored in the spring as elastic potential energy. If you let go, the spring can move. It can push or pull another object. It can convert stored energy into kinetic energy. If friction is present, some energy becomes heat. Again, the system changes. Again, the accounting matters. This is why energy is not simply power. In everyday speech, people often mix energy, force, power, heat, and electricity. But in physics, these words have different meanings. Force is an interaction that can change motion. Work is energy transferred by a force acting through a distance. Power is the rate at which energy is transferred or transformed. Heat is energy transferred because of temperature difference. Temperature is related to the average microscopic kinetic energy of particles in a material. Internal energy is the total microscopic energy stored within a system. These words are connected, but they are not the same. A weak heater, running for a long time, can transfer a large amount of energy. A powerful engine can transfer energy very quickly. A hot object has thermal energy, but heat refers to energy crossing a boundary because of a temperature difference. A force can act without doing work if there is no movement in the direction of the force. A battery stores energy, but power depends on how quickly that energy is delivered. These distinctions may sound small, but they are the difference between cloudy language and real physics. Science often begins by sharpening words, not to make them cold, but to make them useful. Energy becomes powerful because it can be measured and calculated. The unit of energy in the international system is the joule. 1 joule is a small amount of energy. Lifting a small apple by about 1 meter takes roughly 1 joule of work. A food calorie, the kind used on nutrition labels, is actually it is about 4,184 joules. A human body uses millions of joules of energy each day, drawn from chemical energy stored in food. An electric bill measures energy in kilowatt-hours. 1 kilowatt-hour is the energy transferred by 1,000 watts of power over 1 hour. That is 3,600,000 joules. These numbers remind us that energy is not vague. It has units. It can be counted. It can be compared. It can be paid for. It can be stored in fuel. It can be lost as waste heat. It can be delivered through wires. It can be carried by light. It can be measured in laboratories. When people use the word energy loosely, they often make it mysterious. But the scientific meaning is more impressive because it works. It lets engineers design engines. It lets meteorologists study weather. It lets biologists understand metabolism. It lets chemists calculate reactions. It lets astronomers understand stars. It lets doctors use imaging technology. It lets us understand why a refrigerator must release heat into the room, why a car engine becomes hot, why exercise warms the body, why a falling object speeds up, why a planet orbits, why sunlight can become wind, rain, plant growth, and food. Energy is not one thing with one appearance. It is one quantity appearing through many physical forms. A beam of sunlight crossing space carries electromagnetic energy. When that light reaches a leaf, some of it can be absorbed by molecules. Photosynthesis converts part of that energy into chemical energy. The plant stores energy in molecular bonds. An animal eats the plant. Digestion breaks molecules down. Cells transfer energy into forms the body can use. Muscles contract. The body moves. Heat is produced. Eventually, energy spreads into the surroundings. The pathway is long, but every step is physical. Energy does not care whether we call it beautiful. It simply follows the rules, and that is part of its beauty. The same energy accounting that describes a laboratory piston also describes a forest, a thunderstorm, a volcano, a sleeping body, a city at night. Every glowing window is connected to energy transformation somewhere. Coal burning, gas expanding, water falling through turbines, wind turning blades, sunlight striking solar panels. nuclear reactions releasing energy in a reactor. The light in a room is the final whisper of a long physical chain. That chain can be studied, calculated, improved, measured. This is why thermodynamics became so important. It gave scientists a way to describe systems without tracking every molecule individually. A cup of tea contains an enormous number of molecules. A gas in a cylinder contains more particles than the mind comfortably imagines. We cannot follow every collision one by one, but thermodynamics lets us describe the whole system using macroscopic quantities: temperature, pressure, volume, internal energy, heat, work. These quantities allow us to understand matter at large scales. Thermodynamics is not vague. It is not hand-waving. It is a disciplined science of averages, totals, boundaries, and transformations. To use thermodynamics, we choose a system. That system might be gas inside a cylinder, water in a kettle, a human body, Earth's atmosphere, a star. Everything outside the system is called the boundary between system and surroundings may be real, like the wall of a container, or imaginary, like the surface around a region of air we are studying. Energy can cross that boundary. It may cross as heat, it may cross as work, it may cross as matter, if the system is open. But the accounting depends on being clear about what system we are discussing. This is another reason vague energy language fails. It usually has no system, no boundary, no unit, no measurement, no conservation equation, no way to test the claim. In real science, we ask better questions. What is the system? What energy enters? What energy leaves? What work is done? What heat is transferred? How does internal energy change? These are quiet questions, but they are strong. They turn confusion into calculation. Now, when we say energy is conserved, we do not mean it always stays in the same form. A common misunderstanding is to imagine energy as a fixed little object that travels unchanged. But energy can transform completely. The chemical energy in wood becomes heat, light, sound, smoke, motion, and molecular rearrangement. The gravitational potential energy of falling water becomes kinetic energy, turbine rotation, electrical energy, and eventually heat. The nuclear energy in the sun becomes light, solar heating, weather patterns, plant chemistry, and living metabolism. The form changes, the total account remains. That is the thread connecting everything. Energy conservation does not mean nothing changes. It means change is constrained. It means the universe does not allow physical processes to spend energy that was never available. It means every transformation has a cost and a source. This is why the first law is so important. It gives us a way to follow energy through change. Before we write the formula, we need these ideas ready. Energy is measurable. A system has internal energy. Heat is energy transfer due to temperature difference. Work is energy transfer through organized action. A process changes the energy of a system depending on what enters and leaves. Then the first law becomes almost natural. It is not a spell, not a slogan, not a dusty equation. It is an accounting statement for physical reality. If energy enters a system as heat, the system's internal energy may increase. If the system does work on its surroundings, it gives energy away. If work is done on the system, its energy may increase. If heat leaves, its energy may decrease. The details depend on sign conventions, but the principle is clear. Energy changes form and crosses boundaries, but it is not created from nothing, and it is not destroyed into nothing. This is the scientific meaning behind the word energy, not a mood, not a glow, not a personality, not a vague field of intentions, a measurable quantity that connects the motion of planets, the warmth of tea, the chemistry of cells, the burning of fuel, the shining of stars, and the turning of engines. A quiet thread running through the machinery of nature. And once we understand what energy really means, we are ready to meet the three words that make the first law come alive. Heat, work, internal energy. They are simple words, but inside them is the structure of thermodynamics, and in the next scene, we will open them slowly. Before the first law of thermodynamics can feel clear, we need three words. Heat, work, internal energy. They sound ordinary, almost too ordinary. But in thermodynamics, these words are not casual, they are precise. They tell us how energy crosses the boundary of a system, and how energy is stored inside that system. A system can be almost anything we choose to study. Gas inside a cylinder, water in a kettle, air in a room, a car engine, a human body, a planet's atmosphere. The system is the part of the universe we focus on. Everything outside it is the between them, there is a boundary. Sometimes the boundary is physical. The wall of a container, the skin of a balloon, the metal surface of an engine cylinder. Sometimes it is imaginary, a region of air drawn in our mind, a volume of ocean, a parcel of gas in the atmosphere. But once we choose the system and its boundary, we can ask a disciplined question. How does energy cross that boundary? There are two main ways in the first law: heat and work. Internal energy is what changes inside. Let us begin with heat. In everyday speech, people often say an object contains heat. But in thermodynamics, heat is not something an object contains. Heat is energy in transit, energy transferred from one system to another because of a temperature difference. A hot cup of tea sitting in a cooler room transfers energy to its surroundings as heat. The tea cools, the air warms slightly. The cup warms, the table may warm a little. Infrared radiation carries energy away. The energy crosses boundaries because the tea is hotter than its surroundings. That transfer is heat. Once the energy is inside the surroundings, we do not call it heat anymore. It has become part of the surroundings' internal energy, or it may move onward again. Heat is a process, a transfer, a crossing, not a substance. This is important. A hot object has internal energy. It may transfer some of that energy as heat, but heat itself is not a fluid sitting inside the object. Historically, people once imagined something like that, a heat fluid called caloric, but modern thermodynamics and statistical mechanics replaced that picture. Heat is not a mysterious, invisible liquid. It is energy transfer due to temperature difference. That quiet correction matters, because it turns fog into physics. Now, what is temperature? Temperature is related to the average microscopic kinetic energy of particles in a substance. In a gas, molecules move rapidly. They collide. They fly in different directions. The higher the temperature, the faster they move on average. In a solid, atoms and molecules vibrate around positions. In a liquid, particles move, rotate, collide, and rearrange. Temperature is not exactly the total energy of the system. A bathtub of warm water can contain much more internal energy than a tiny spark, even if the spark is much hotter. Temperature is about average microscopic energy. Internal energy is about the total microscopic energy stored in the system. So heat and temperature are connected, but not the same. Heat is energy transfer. Temperature helps determine the direction of that transfer. Energy as heat naturally flows from hotter systems to colder systems when they are in thermal contact. A hot spoon in a cool room loses energy. A cold drink in a warm room gains energy. A warm body under a blanket slows heat loss. A refrigerator moves energy from a colder interior to a warmer room by using work. The details can become rich, but the basic idea is simple. Temperature difference drives heat transfer. Now let us turn to work. In thermodynamics, work is another way energy crosses a system boundary. Work occurs when a force acts through a distance, or more generally when organized macroscopic action transfers energy. A gas expanding inside a cylinder can push a piston upward. The gas exerts a force. The piston moves. The gas does work on the piston. Energy leaves the gas and goes into the surroundings as a mechanical motion. If the piston compresses the gas instead, the surroundings do work on the gas. Energy enters the gas. Its internal energy may increase. Its temperature may rise. This is the heart of many engines, machines: expansion, compression, pressure, volume, motion. A steam engine uses expanding steam to push a piston. An internal combustion engine uses hot expanding gases to move pistons. A bicycle pump warms when you compress air inside it. Why? Because you do work on the gas. You push molecules into a smaller volume. Their microscopic energy increases. The air temperature rises. That warming is not mystical. It is mechanical energy becoming internal energy. Work is not limited to pistons. A battery can do electrical work in a circuit. A motor can do mechanical work. A stretched rubber band can do work when it snaps back. A person can do work lifting a box. A compressor can do work on a gas. A pump can do work moving water. Work is energy transferred in an organized way. Heat is energy transferred because of temperature difference. Both can change internal energy. Now internal energy is the energy contained within a system at the microscopic level. It includes the kinetic energy of molecules moving, rotating, and vibrating. It includes potential energy from interactions between particles. In some systems, it includes energy stored in molecular arrangements, phase changes, chemical bonds, and other microscopic structures. For an ideal gas, internal energy is closely related to temperature because particles are treated as non-interacting, except in collisions. For real substances, internal energy can involve much more: liquids, solids, phase changes, molecular bonds, interactions, vibrations. Internal energy is not directly visible. You do not look at a cup of tea and see its internal energy written on the surface, but you can infer changes in internal energy from heat transfer, work, temperature change, phase change, and other measurable quantities. If you heat water, its internal energy increases. If the water begins to boil, added energy goes into changing phase from liquid to vapor, as well as changing molecular motion. If gas expands and does work, its internal energy may decrease unless heat is added. If you compress gas quickly, internal energy can increase and temperature can rise. This is why thermodynamics is so practical. It lets us track energy without following every molecule. No one watches each molecule in a cylinder and writes down its personal diary. That would be a very long book, a molecule memoir with too many collisions. Instead, thermodynamics uses macroscopic quantities: temperature, pressure, volume, internal energy, heat, work. These allow us to understand the whole system. Now, the first law will connect these ideas. But before writing it, let us feel the logic. Imagine a sealed cylinder full of gas with a movable piston. This gas is our system. If we heat the cylinder from below, energy enters the gas as heat. The molecules move faster on average. The internal energy increases. The gas may expand. If the piston moves outward, the gas does work on its own. Some of the energy entering as heat leaves as work. If the piston is locked, the gas cannot expand. The added heat mostly increases internal energy and temperature. If the gas expands while no heat is added, it may use its own internal energy to do work. Its temperature can drop. Same gas, different boundary conditions. Different energy accounting. This is the elegance of thermodynamics. It does not just ask what something is made of. It asks what can cross the boundary, what is added, what is removed, what changes inside. A system is like a quiet room with doors. Heat may enter through one door, work may leave through another. Internal energy is what changes inside the room, but the accounting must balance. If more energy enters than leaves, internal energy rises. If more energy leaves than enters, internal energy falls. If energy enters as heat and leaves as work in equal amounts, internal energy may stay the same. Different processes, same principle. Now consider something familiar. A person rubbing their hands together on a cold night. Mechanical work is done by muscles moving the hands. Friction converts organized motion into microscopic thermal motion. The hands warm. Energy from chemical processes in the body becomes mechanical motion, then internal energy in the skin. It feels like heat, but the pathway matters. Or think of brakes on a bicycle. The moving bicycle has kinetic energy. When the brakes press against the wheel, friction does work against the motion. The bicycle slows. The brake pads and wheel warm. Organized motion becomes internal energy. Energy is not destroyed. It becomes less organized thermal motion. That loss of usefulness points toward the second law, but the conservation is first law territory. Or think of a refrigerator. Inside, it removes energy from the cold compartment, but heat does not naturally flow from cold to warm by itself. The refrigerator uses electrical work to move energy from the inside to the warmer room. That is why the back of a refrigerator becomes warm. It releases the removed energy plus the energy supplied as electrical work. Again, bookkeeping. Input, output, transfer, transformation. The first law is everywhere. Once these three words are clear, heat, work, internal energy. But we should also be careful with signs. Different textbooks use different sign conventions. Some write the first law as change in internal energy equals heat added to the system minus work done by the system. Others write it as change in internal energy equals heat added to the system plus work done on the system. These are not different laws. There are different accounting choices. The physical message is the same. Energy added to a system increases its internal energy unless energy leaves in another form. Energy removed from a system decreases its internal energy unless energy enters elsewhere. Work done by a system costs the system energy. Work done on a system gives it energy. Heat entering gives it energy. Heat leaving takes energy away. The signs are bookkeeping symbols. The reality is transfer. This matters because equations can look intimidating, but the first law is not trying to frighten anyone. It is a calm statement. If the system changes, energy has been transferred or transformed. If energy crosses the boundary, the internal energy account changes. If work is extracted, it must come from somewhere. If heat is added, it must go somewhere. No free energy machine can sneak past this law wearing a fake mustache. Nature checks the books. That is why the first law has such authority. It is not an opinion about energy. It is a pattern confirmed across heat engines, chemical reactions, electrical systems, biological systems, and astronomical processes. It is built into the way physics describes change. Now, let us return to the popular confusion. When someone says energy is everything, they may be saying something poetic, but physics asks a sharper question. What kind of energy? In what system? Measured how? Transferred by heat, work, radiation, matter, flow, or another mechanism. Stored in what form? Changed by what process? Balanced by what equation? Without those questions, the word energy becomes a fog machine. With those questions, it becomes science. Thermodynamics gives us the questions. It gives us a way to study change without pretending. A hot gas expanding, a kettle boiling, a body metabolizing food, a planet absorbing sunlight, a star radiating into space. Each one can be described by energy crossing boundaries and internal energy changing. Heat and work are not vibes, they are transfer mechanisms. Internal energy is not mood, it is microscopic physical energy stored in the system. This is the real structure, quiet, exact, useful, and more beautiful than the fog, so we are ready to write the law. Not as a decorative formula, not as a classroom relic, but as the central accounting rule behind engines, bodies, weather, and stars. The first law of thermodynamics says that the change in a system's internal energy equals the energy added as heat minus the energy the system gives away as work, a small equation, a vast meaning. And in the next scene, we will open that equation carefully, one piece at a time. Now we are ready to write the first law of thermodynamics, not as a spell, not as a slogan, not as a mystical sentence about energy floating through life, but as an accounting rule, a precise statement about what happens when energy enters, leaves, or changes form inside a physical system. One common way to write it is this: the change in internal energy equals the heat added to the system minus the work done by the system. In symbols, it is often written as delta U equals Q minus W. Delta U is the change in internal energy. Q is heat added to the system. W is work done by the system on its surroundings. A small equation, a quiet equation, but inside it is an enormous part of physical reality. If heat enters the system gains energy. If the system does work on the outside world, the system gives energy away. Whatever remains changes the system's internal energy. That is the first law. It says the books must balance. Let us take a simple cylinder of gas. A piston sits on top. The gas inside is our system. The flame beneath the cylinder warms the gas. Energy enters the gas as heat. The molecules move faster. They collide with the piston more strongly. The gas expands. The piston rises. As it rises, the gas does work on the surroundings. Some of the energy that entered as heat becomes mechanical work. Some may remain in the gas as increased internal energy. The accounting depends on the details. How much heat enters, how far the piston moves, how much pressure is involved, how much the temperature changes. But the principle is fixed. Energy entering as heat must be accounted for. Energy leaving as work must be accounted for. The internal energy changes by the difference. This is the clean heart of the first law. Energy is not created by the gas. Energy is not destroyed by the piston. It is transferred, transformed, counted. The same law applies if we reverse the process. Suppose we push down on the piston. Now, the surroundings do work on the gas. The gas is compressed. Its molecules are forced into a smaller volume. Their microscopic motion may increase. The temperature may rise. Energy has entered the gas through work done on it. Depending on the sign convention, we may write this differently. But physically, the meaning is clear. Work done on a system can increase its internal energy. Work done by a system can decrease its internal energy. Heat added can increase it. Heat removed can decrease it. The system is not allowed to cheat. Now let us slow down and look at the symbols. Delta U, QW, delta U is not the total internal energy itself. It is the change in internal energy. A system may begin with one internal energy and end with another. The difference is delta U. If the system ends with more internal energy than it began with, delta U is positive. If it ends with less, delta U is negative. Internal energy belongs to the state of the system. For a simple gas, it is related to the microscopic motion of particles. For more complex systems, it may include molecular interactions, vibrations, rotations, chemical structures, and more. But in thermodynamics, we often care about changes. How much did the internal energy increase? How much did it decrease? That is what delta U tells us. Q is heat. But again, heat is not something stored inside the system. Q represents energy transferred across the boundary because of temperature difference. If heat flows into the system, Q is positive in this convention. If heat flows out, Q is negative. A hot plate warming a pot of water adds heat to the water. A warm cup cooling in a room loses heat to the surface. Heat is energy crossing a boundary. W is work done by the system. If the gas expands and pushes a piston, the system does work. Energy leaves the system in an organized mechanical way. In the convention delta, U equals Q minus W, work done by the system is subtracted, because it is energy going out. If work is done on the system instead, then W may be negative in this convention, and the internal energy increases accordingly. This is why signs can confuse beginners. but the signs are only bookkeeping directions. The physical idea is simpler. Energy entering increases the system's account. Energy leaving decreases it. Heat and work are transfer methods. Internal energy is the account inside. Now, let us try a quiet example. Imagine a sealed rigid container of gas. The container cannot expand. Its walls do not move. No piston. No change in volume. If we add heat to the gas cannot do expansion work on the surface. So, in a simple case, the energy added, as heat increases, the internal energy of the gas. The temperature rises. The molecules move faster, on average. Here, Q enters. W is 0. Delta U equals Q. All the added heat stays in the system as increased internal energy. Now imagine a gas inside a cylinder with a movable piston. We add the same amount of heat, but this time, the gas expands and pushes the piston. The system does work. Some energy leaves as work. Less energy remains as increased internal energy. The temperature may rise less than in the rigid container. Here, Q enters. W leaves. Delta U equals Q minus W. Same heat input, different boundary, different result. This is why thermodynamics cares so much about the system and its constraints. Locked container or movable piston. Insulated wall or conducting wall. Slow expansion or rapid expansion. Constant volume or constant pressure. Each condition changes the energy accounting. The law is the same. The pathway differs. Now consider an insulated gas expanding. Suppose no heat enters or leaves. The system is thermally insulated. Q is 0. If the gas expands and does work on the surroundings, energy must come from somewhere. It comes from the gas's internal energy. Delta U becomes negative. The gas cools. This kind of process is called adiabatic, when no heat is exchanged. Adiabatic processes are important in engines, weather, and atmospheric physics. Air rising in the atmosphere expands because pressure decreases with altitude. As it expands, it does work on the surrounding air. If little heat is exchanged during the process, the air cools. This cooling helps clouds form. A thermodynamic law quietly shapes the sky. Now consider compression. When air is compressed quickly, work is done on it. Energy enters as work. Its internal energy increases. Temperature rises. This is why a bicycle pump can become warm when used rapidly. You are doing work on the air. The air becomes warmer. Not because of mystical energy, not because of hidden fire. Because mechanical work has increased internal energy. The first law is sitting in your hand, inside a bicycle pump. Now consider food. The human body is a thermodynamic system, though a very complex, open one. Food contains chemical energy. Cells transform that chemical energy through metabolism. Some becomes used for work. Muscle contraction, ion pumping, molecular synthesis, brain activity. Some becomes heat. The body maintains temperature by balancing energy input, work, heat loss, and stored chemical energy. The body is not a perpetual motion machine. It cannot produce motion, warmth, and biological maintenance without energy input. It must eat, it must breathe, it must release waste heat. The first law does not stop at machines. It applies to life. Life is not outside physics. Life is a beautifully organized physical process. Now consider a power plant. Fuel is burned. Chemical energy becomes thermal energy. Water turns into steam. Steam expands through turbines. Turbines turn generators. Electricity flows through wires. Waste heat leaves into cooling systems or the environment. At every stage, the first law attracts energy. The energy output cannot exceed the energy input. And in practice, not all input energy becomes useful electrical work. Some leaves as waste heat. The first law says energy is conserved. The second law explains why not all energy can be converted into useful work. But the first law gives the accounting. How much came in? How much went out? Where did the rest go? Now think of a car engine. Fuel enters. Air enters. Combustion releases energy from chemical bonds. Hot gases expand. Pistons move. The crankshaft turns. The car moves. Heat escapes through exhaust. Heat warms the engine block. Heat leaves through the radiator. Sound is produced. Friction warms parts. Only some of the fuel's energy becomes useful motion of the car. The rest is still energy. It has not vanished. It has spread into forms less useful for moving the vehicle. The first law tells us it must be somewhere. The second law tells us why so much of it becomes waste heat. This is why real energy science is stricter than popular energy talk. In vague language, energy can seem endlessly available. A word that can mean anything. A mood, a signal, a feeling, a vibration, a force of intention. But in thermodynamics, energy must be accounted for. What entered, what left, what changed, what boundary did it cross, what work was done. what heat was transferred. No clear system, no clear claim, no measurement, no physics. This is not less beautiful, it is more beautiful, because it lets us understand the machinery of reality. Now let us examine the phrase, conservation of energy. It does not mean a system's internal energy never changes. That is a common mistake. A system's internal energy can rise or fall. A cup cools, gas heats, a battery drains, a body burns food, a star radiates energy. The system changes. Conservation means that when we include all transfers and transformations, the total energy accounting balances. If one system loses energy, another gains it. If energy leaves as work, it appears in this. If energy leaves as heat, it becomes internal energy somewhere else, or radiation traveling through space. If chemical energy decreases, it becomes heat, work, light, electrical energy, or other forms. Energy is not frozen, it is conserved through change. That is the key. Conservation does not mean stillness, it means lawful transformation. The first law is not saying nothing happens, it is saying that when something happens, energy is never allowed to disappear from the story. Every physical event has an energy budget. A match burning, a candle melting, a storm forming, a laptop warming, a kettle boiling, a person walking, a planet cooling, a star shining. Each has an account. Energy enters, energy leaves. Energy changes form, the balance remains. Now, the first law is sometimes stated for isolated systems. In an isolated system, no energy or matter crosses the boundary. For such a system, the total energy remains constant. But many systems we study are not isolated. They exchange heat, they do work, they receive work, they lose energy, they gain energy. The first law still applies. It tells us how internal energy changes depending on the transfers. This flexibility makes it powerful. We can use it for a closed container, a piston, a chemical reaction, a living organism, a weather pattern, an engine, a refrigerator, a star. The details differ, but the accounting principle remains. Now let us return to the formula one more time. Delta U equals Q minus W. If Q is positive, heat enters the system. If W is positive, the system does work on the internal energy change is what remains. If Q is larger than W, internal energy increases. If W is larger than Q, internal energy decreases. If Q equals W, internal energy does not change, even though energy flowed through the system. This last point is important. A system can transfer energy without changing its internal energy overall. For example, in a steady engine cycle, the working substance may return to its original state after each cycle. Its internal energy change over a full cycle is zero. But during that cycle, heat entered, work was produced, and heat was rejected. The system did not create energy. It converted part of incoming heat into work and expelled the rest. This is how engines become possible. Cycles, transfers, returns, accounting. The first law is the first guardian at the gate. It says no machine can give more energy than it receives. But it does not say every received unit of energy can become useful work. That deeper limitation belongs to the second law. For now, the first law is enough to defeat one old fantasy, a perpetual motion machine of the first kind. This is a machine that would produce work forever without energy input, or produce more energy than it consumes. The first law says no. Not almost, no. Not probably, no. No, unless our understanding of physics is overturned in a very specific and extraordinary way. A device that claims to create energy from nothing is making a claim against one of the deepest conservation principles in science, and extraordinary claims need extraordinary evidence, not a blurry video, not a spinning wheel in a dark room, not a confident sales pitch. A clear energy account, input, output, measurement, losses, controls, reproducibly. The universe keeps the books, and the books do not accept vibes. This is the practical strength of the first law. It protects science from sloppy language. It protects engineering from impossible promises. It helps us design machines that work, instead of dreaming about machines that cannot. It helps us understand why fuel matters, why waste heat matters, why insulation matters, why efficiency matters, why energy storage matters, why power grids matter, why metabolism matters, why climate matters. The law is not abstract only, it touches civilization. Every engine, every heater, every refrigerator, every battery, every power plant, every solar panel, every organism, every atmosphere lives under its quiet rule. Energy cannot be wished into existence. Energy cannot be marketed into existence. Energy cannot be spiritually negotiated into existence. It must come from a physical source, and when it changes form, the account must balance. This may sound strict, but it is also comforting, because it means the world is intelligible. A flame does not burn by mood, a motor does not turn by intention, a star does not shine by metaphor. They all participate in lawful transformation. Once we understand the first law, we begin to see hidden ledgers everywhere. In a cup cooling beside the bed, in clouds forming above a dark ocean, in the warmth under a blanket, in the hum of a refrigerator at night, in the battery of a phone, in the slow glow of the sun beyond Earth's horizon. The same law whispers through all of them. Energy enters, energy leaves, energy changes form, the account balances. And now that we have opened the first law itself, we can ask a sharper question. Why can energy not be created from nothing? Why do impossible machines fail? Why does every real process need a source, a transfer, and a cost? That question takes us deeper into conservation, and into the quiet refusal of nature to give something for nothing. One of the oldest dreams in the history of machines is the dream of free energy, a wheel that turns forever, a device that powers itself, a motor that produces more energy than it consumes, a machine that runs without fuel, without input, without loss, and without cost. It is an attractive dream, quietly seductive, a little wheel in the corner of the room, spinning forever, a generator that never needs feeding, a universe that gives something for nothing. But the first law of thermodynamics stands at the door and says no. Not loudly, not angrily, just firmly. Energy cannot be created from nothing. If a system produces work, that energy must come from somewhere. If a lamp glows, energy is being supplied. If a motor turns, energy is being transferred. If a heater warms a room, energy is entering the room or being transformed within it. If a machine keeps moving, something is feeding the motion, or the motion is slowing down. The account must balance. This is where real science separates itself from showmanship. A person can claim that a machine creates energy, but physics asks for the account. What is the system? What are the inputs? What are the outputs? What is the energy stored before and after? What losses are present? How is heat measured? How is work measured? Can the result be repeated? Can independent observers verify it? Where is the energy coming from? Without those questions, the claim is only theater wearing a lab coat. The first law does not forbid imagination. It forbids bad accounting. Consider a simple electric motor connected to a battery. The motor spins. It may lift a weight. It may turn a fan. It may drive a small wheel. At first glance, one might focus only on the motion. The wheel is turning, the fan is blowing. The system looks alive, but the battery is being drained. Chemical energy inside the battery is being converted into electrical energy, mechanical work, and heat. The motor warms. The wires may warm. The air moves. Sound is produced. If the battery runs down, the motor stops. Nothing mysterious has happened. Energy was stored. Energy was transferred. Energy was transformed. The account was paid. Now imagine someone hides the battery, or hides the power cable, or ignores the warmth of the motor, or measures only the useful output while forgetting the losses. Then the machine may seem more impressive than it is. This is why careful measurement matters. Nature does not care which part of the device we pay attention to. The energy account includes all of it. Useful work, waste heat, friction, sound, vibration, electrical resistance, stored energy, chemical change, every quiet little leak, every warm bearing, every humming wire, every imperfect surface. The books include the small print. Perpetual motion machines of the first kind are machines that would create energy from nothing. They would produce work indefinitely without an energy source. The first law rules them out. A machine can keep moving for a long time if losses are small. A planet can orbit for billions of years because space offers very little resistance. A spinning object in a vacuum can continue for a long time. A superconducting current can persist because electrical resistance is extremely low. But long-lasting motion is not the same as creating energy. Low loss is not free creation. Persistence is not production. That distinction matters. A pendulum can swing for many cycles, but friction with air and internal material losses slowly reduce its motion. Energy becomes heat in the air, the support, and the pendulum itself. The swing shrinks. Eventually, it stops. If we want it to keep swinging, we must add energy. A clock does this. A pendulum clock uses energy from a wound spring or a falling weight. A quartz clock uses a battery. The timing may look effortless, but something is paying. Always. Now think of a spinning wheel. If the bearings are excellent and the air resistance is low, it may spin for a long time, but tiny losses remain. Friction in the bearings, air drag, vibrations, sound, heat. Energy moves from organized rotation into microscopic motion. The wheel slows. To keep it spinning forever, energy must be added. To make it produce useful work while also spinning forever without input would require energy from nowhere. And that is exactly what the first law does not allow. This is why every real power source has a source. A hydroelectric dam uses gravitational potential energy of water. The sun lifted that water earlier through evaporation in the water cycle. A wind turbine uses kinetic energy of moving air. The wind is driven by uneven solar heating of Earth. A coal plant uses chemical energy stored in ancient plant matter. That energy originally came from sunlight, captured by photosynthesis millions of years ago. A nuclear reactor uses energy from changes in atomic nuclei. A solar panel uses electromagnetic energy arriving from the sun. A battery uses stored chemical energy. Food uses chemical energy stored in molecules, much of it ultimately linked to sunlight. Even when the chain is long, energy comes from somewhere. There is always a physical source. This is the real meaning of energy conservation. Not that energy is easy. Not that energy is equally useful in every form. Not that energy is available just because we want it, but that every transfer and transformation must be connected to a source and a destination. The dream of free energy often survives by hiding part of the chain. It focuses on the output and forgets the input. It counts the motion and ignores the heat. It counts the electricity and ignores the fuel. It counts the spinning and ignores the stored energy. It counts the useful work and ignores the environment. But thermodynamics widens the camera. It asks us to include the whole scene. The machine, the battery, the room, the heat, the friction, the chemical changes, the wires, the fuel, the exhaust, the surroundings. Once the whole system is included, the miracle usually becomes an accounting mistake. This is not cynicism, it is scientific care. Science is not against wonder. It is against confusion disguised as wonder. A real solar panel is wonderful. It turns sunlight into electrical energy through the physics of semiconductors. A real wind turbine is wonderful. It extracts energy from moving air shaped by Earth's atmosphere. A real battery is wonderful. It stores chemical energy and releases it through controlled electrochemical reactions. A real heat engine is wonderful. It converts part of thermal energy into mechanical work. We do not need impossible machines to feel amazement. Working machines are already astonishing. They are not less beautiful because they obey the first law. They are beautiful because they obey it so precisely. Now, there is another popular confusion. People sometimes say, energy can be created by intention, emotion, or belief. In ordinary language, we may understand what they mean. A motivated person may feel energetic. A peaceful room may feel calming. A crowd may feel intense. But these are psychological, social, or emotional descriptions. They are not thermodynamic energy. A feeling of energy in the body involves biology, nervous system activity, hormones, metabolism, blood flow, sleep, nutrition, muscle readiness, brain chemistry. A person who feels energetic is not violating physics. Their body is using chemical energy from food and oxygen. Cells are producing ATP. Muscles and neurons are active. Heat is generated. The body is doing thermodynamic bookkeeping every second. So even the feeling has a physical basis. But the feeling is not the same as creating energy from nothing. If the body does work, it uses energy. If the brain remains active, it uses energy. If muscles contract, they use energy. If body temperature is maintained, energy is being transformed and released as heat. There is no special exemption for life. Life is not outside thermodynamics. Life is thermodynamics organized beautifully. The same is true for technology. A phone does not run on intention, it runs on battery chemistry. A lamp does not glow because the room deserves light. It glows because electrical energy is transferred and transformed into light and heat. A car does not move because motion is inspirational. It moves because fuel or stored electrical energy is converted into mechanical work. With losses, the first law removes the costume. It asks what is physically happening. This can feel less romantic at first, but the romance returns in a better form. Because now the world becomes connected. Your body's warmth is connected to food. Food is connected to plants. Plants are connected to sunlight. Sunlight is connected to nuclear fusion in the sun. The sun is connected to gravity, plasma, pressure, and nuclear physics. The warmth in your hands is part of a long chain of energy transformations beginning in a star. That is not vague energy talk. That is real energy, and it is more beautiful than the fog. Now, why exactly can energy not be created from nothing? At the level of classical thermodynamics, it is a conservation law. Energy is conserved. This principle has been tested across enormous ranges of phenomena: mechanical systems, thermal systems, chemical reactions, electrical circuits, nuclear processes, astronomical systems. In modern physics, conservation of energy is connected to a deep symmetry. The laws of physics do not change from one moment to the next in ordinary conditions. This time translation symmetry is related, through Noether's theorem, to conservation of energy. We do not need to go deeply into the theorem tonight, but it is worth knowing that energy conservation is not just a rule someone noticed in engines. It is tied to the structure of physical law. If the rules of nature are the same today as they were yesterday, energy conservation appears as a deep consequence in the mathematical description. That is a remarkable idea. The quiet account of energy is linked to the steady rhythm of time itself. Still, in cosmology and general relativity, energy can become more subtle. For example, in an expanding universe, defining total energy for the whole universe is not always straightforward in the same way as for a simple engine or box of gas. Light traveling through expanding space can be redshift. The bookkeeping becomes more delicate, but for ordinary thermodynamic systems, engines, bodies, machines, laboratories, and daily physical processes, the first law remains one of the most reliable tools we have. This nuance matters. Real science is strong enough to include nuance. We do not need to oversimplify conservation into a cartoon. For the systems we are studying in thermodynamics, energy cannot be made from nothing. And any claim that a machine produces usable energy without an input must face the first law. Now, suppose someone presents a device. A wheel turns, a light glows, a meter moves. The claim is that the device powers itself. What should we ask? First, what is the complete system boundary? Second, what are all possible inputs? Electrical input, chemical input, mechanical input, magnetic interactions, thermal gradients, stored energy, batteries, compressed springs, hidden fuels, environmental energy. Third, what are all outputs? Mechanical work, electrical output, heat, sound, light, vibration, chemical change. Fourth, how long does it run? Is energy storage being depleted? Is the temperature changing? Are materials being consumed? Is the measurement calibrated? Can independent laboratories reproduce it? This is not being close-minded. This is how reality is checked. The first law is not defeated by surprise. It is tested by measurement. If a device truly created energy from nothing, it would not be a small curiosity. It would overturn one of the deepest principles of physics. It would reshape engineering, cosmology, chemistry, and thermodynamics. Such a discovery would require extraordinary evidence. Clear, repeatable, measured, public, careful, not hidden behind vague claims. And until such evidence exists, the first law remains undefeated, quietly sitting at the desk, adding the numbers. Now, there is a gentle lesson here, beyond machines. Energy is precious because it must come from somewhere. Useful energy especially. To heat a home, energy must be supplied. To cool a room, energy must be moved. To power a city, energy must be generated from physical sources. To run a body, food and oxygen must be transformed. To launch a spacecraft, fuel, or another energy source must be used. There is no shortcut around the account. This is why energy efficiency matters. If we cannot create energy from nothing, we must use available energy wisely. We can reduce losses, improve insulation, design better engines, build better batteries, capture sunlight, use wind, use geothermal heat, improve power grids, recover waste heat, reduce friction, improve materials. The first law does not make engineering hopeless. It makes engineering honest. It tells us what cannot be done, so we can focus on what can. And what can be done is already extraordinary. A turbine blade shaped carefully enough to extract energy from steam. A photovoltaic cell turning sunlight into current. A heat pump moving warmth from cold outdoor air into a home. A battery storing chemical potential for later use. A human body transforming breakfast into thought, motion, and warmth. These are not violations of thermodynamics. They are thermodynamics made useful. The first law does not kill invention. It guides it. It says, do not promise energy from nowhere. Find the source, understand the transfer, measure the losses, respect the boundary, then build. That is a better kind of dream. A dream with bolts, equations, sunlight, and truth. So when we say energy cannot be created from nothing, we are not making the universe dull. We are giving it structure. A universe where every fire has fuel, every motion has a source, every machine has an input, every body has metabolism, every star has nuclear processes, every transformation has a ledger. The strictness is the beauty, because the ledger connects everything. The ember in a stove, the steam in an engine, the sugar in a cell, the current in a wire, the wind above the sea, the sunlight on a leaf, the glow of a distant star. Different forms. 1. Accounting. The first law does not ask us to believe in energy. It asks us to measure it. And once we measure it, we discover that the real world is not less mysterious. It is more deeply connected. In the next scene, we will return to the history of heat engines. To fire, steam, pistons, factories, and the practical questions that gave birth to thermodynamics. Because the first law did not emerge from vague philosophy. It emerged from the stubborn, smoky, mechanical problem of turning heat into work. Thermodynamics was not born as a vague idea about energy. It was born in heat, in fire, in steam, in metal, in pressure, in engines that hissed, shook, warmed, leaked, and worked. Before thermodynamics became a clean set of laws in textbooks, it was a practical problem. People wanted to know how to turn heat into motion, how to pump water from mines, how to move pistons, how to turn wheels, how to power factories, how to get useful work from fuel. The question was not mystical, it was mechanical. If we burn coal, water becomes steam. If steam expands, it can push. If it pushes a piston, a wheel can turn. If the wheel turns, a machine can work. But how much work can we get? Where does the heat go? Why does some energy become useful motion, while so much escapes as waste heat? Why do engines become hot? Why can no engine turn all heat into perfect work? These questions were not decorative. They mattered to miners, engineers, factory owners, inventors, scientists, cities, railways, ships. The Industrial Revolution did not run on abstract slogans. It ran on fuel, boilers, pistons, pressure, and energy transformations. Thermodynamics grew from the need to understand those transformations. The steam engine is one of the great physical teachers. It takes thermal energy from burning fuel and uses it to heat water. Water becomes steam. Steam expands. Expanding steam pushes a piston. The piston does mechanical work. Some energy becomes motion. Some remains as internal energy. Some leaves as heat. Some is lost through friction, exhaust, and warming the surrounding machinery. The first law tells us that the energy must be accounted for. Fuel energy does not vanish. Heat does not become work without a trace. Motion does not appear from nowhere. The engine is an energy transformer, not an energy creator. This distinction is the spine of thermodynamics. An engine does not make energy. It converts energy from one form into another. Chemical energy, in fuel, becomes thermal energy. Thermal energy becomes mechanical work. Mechanical work may become motion of a wheel, a pump, or a generator. And along the way, energy spreads into heat, sound, vibration, and exhaust. The machine may look powerful, it may roar, it may shake the ground. It may pull a train across a continent, but it still obeys the quiet account. Energy in, energy out. Energy stored, energy lost as heat. The book's balance. Now, historically, the nature of heat was not always understood clearly. For a long time, many scientists thought heat might be a kind of fluid called caloric. In that older view, hot objects contained more of this fluid, and heat flowed from one body to another, like an invisible substance. This idea was wrong. But it was not foolish for its time. It tried to explain real observations with the concepts available. Science often moves this way. A picture works for a while, then measurements become sharper, then the picture cracks, then a better one replaces it. The caloric theory began to fail because heat behaved in ways that looked connected to motion and work. Friction could produce heat. Compressing a gas could warm it. Doing mechanical work could raise temperature. Heat was not behaving like a conserved fluid. It was connected to energy transfer. This was one of the great turning points. Heat and work were not separate kingdoms. They were linked. They could be converted. A certain amount of mechanical work could produce a certain amount of heat. A certain amount of heat, under the right conditions, could produce mechanical work. The connection was not vague. It could be measured. One of the key historical ideas was the mechanical equivalent of heat. This means that heat and mechanical work are different forms of energy transfer, and a definite amount of work corresponds to a definite amount of heat. Experiments in the 19th century helped establish this connection. Mechanical stirring could warm water. Falling weights could turn paddles inside a container. The water temperature would rise. Work had become internal energy. Motion had become microscopic thermal motion. The result was not magic, it was measurement. The paddle wheel experiment is a beautiful image. Imagine a container of water. Inside it, paddles can rotate. A falling weight turns the paddles. As the paddles turn the water, friction and turbulence occur. The water warms slightly. The falling weight loses gravitational potential energy. That energy becomes motion, then microscopic motion in the water. The temperature rises. The account can be measured. Work becomes internal energy. This is the first law beginning to breathe. No flame is needed, no mystical energy field, just mass, gravity, motion, water, friction, and a thermometer. A quiet experiment showing that heat and work belong to the same physical accounting. This realization reshaped science. It showed that energy is not tied to one form. A raised weight, a moving paddle, warm water, expanding gas, burning fuel. They may look different, but energy connects them. The first law unified them. It said that when we include heat and work properly, the change in internal energy can be tracked. The old boundaries between mechanical motion and thermal phenomena began to soften. Nature had not separated them. Our language had. Thermodynamics repaired the language. Now think again of a steam engine. The fuel burns. The boiler heats. Steam forms. Pressure builds. A valve opens. Steam enters a cylinder. The piston moves. The machine does work. Then steam leaves, carrying energy away. The metal warms. Friction warms, bearings, exhaust carries heat. The engine needs a continuous input of fuel because energy is continuously being transformed and dispersed. If the fuel stops, the engine slows. If pressure falls, the piston weakens. If heat is not supplied, the cycle cannot continue. The machine is honest. It cannot work for free. It can only transform what it receives. This is why the history of thermodynamics is also the history of limits. People did not only want to make engines work, they wanted to make them better, more efficient, less wasteful, more powerful, more reliable, less hungry for fuel. But every improvement faced physical limits. The first law said energy could not be created. The second law would later say that not all heat can be converted into work. Together, these laws turn engineering dreams into measurable constraints, not to kill invention, to guide it. A good engineer does not ask nature for something impossible. A good engineer asks how close a real machine can come to the possible. That question built engines, improved turbines, designed refrigerators, shaped power plants, and eventually helped us understand metabolism, weather, stars, and the universe. Thermodynamics began with steam, but it did not stay there. The same principles apply to a gas expanding in a cylinder and to air rising in the atmosphere, to a boiler heating water and two sunlight warming oceans, to fuel burning in an engine and to food being metabolized in a body, to a piston doing work and to a heart pumping blood, to a turbine turning in a power plant and to a star radiating light into space. The law grew from engines, but it was never only about engines. It was about transformation. Heat into work, work into heat, chemical energy into motion, motion into internal energy, radiation into warmth, energy crossing boundaries, systems changing state, the universe keeping account. This is why the first law feels both practical and profound. It can describe a workshop, and a star, a locomotive, and a living cell, a cup of water, and an atmosphere. The same law walks through all these places wearing different clothes. In a workshop, it smells like oil and steam. In a kitchen, it rises from a kettle. In the body, it moves through metabolism. In the sky, it lifts air and forms clouds. In a star, it rides outward as light. But the principle remains. Energy changes form. Energy crosses boundaries. Energy is conserved. The birth of thermodynamics also teaches us something about how science works. Science does not only come from staring at the stars. Although stars are wonderful, it also comes from dirty machines, from noisy pumps, from mines filled with water, from boilers that must not burst, from engines that waste fuel, from measurements made by people trying to solve practical problems. The laws of nature can be found in brass cylinders and blackened furnaces, and a pressure gauge trembling beside a pipe, in a thermometer rising by a fraction of a degree, in a wheel slowing because friction has warmed its axle. The universe does not only reveal itself in elegant equations, sometimes it reveals itself in soot. This is a lovely thing, because it means real science is not detached from the world. It is born from contact with the world, touching metal, measuring heat, watching steam, listening to engines, noticing loss, asking where the energy went. That question, where did the energy go, is one of the most scientific questions a person can ask. A wheel slows. Where did the energy go? A brake warms. Where did the energy go? A cup cools. Where did the energy go? A battery drains. Where did the energy go? A body tires. Where did the energy go? A star shines. Where did the energy go? The first law teaches us to follow the trail, not with superstition, with measurement. Now, in every engine, there is a system, and the gas in the cylinder may be the system. The piston and rest of the machine also. Heat enters the gas from combustion, or steam. The gas does work on the piston. The gas changes internal energy. Exhaust carries energy away. The engine repeats the process. A cycle, a rhythm, a mechanical breathing. Energy in, work out, heat rejected, return. Again, again, again. This rhythm powered much of modern history. Steam locomotives crossed landscapes, ships crossed oceans, factories turned raw materials into products, pumps drained mines, turbines generated electricity, and behind all of it was the problem of heat and work. The first law became the grammar of that problem. It allowed scientists and engineers to speak clearly. Not that engine has energy in a vague sense, but how much energy enters, how much work is produced. If energy were only mood, it could not move a train. If energy were only spiritual atmosphere, it could not be measured in a boiler. Real energy does work. Real energy changes temperature. Real energy crosses boundaries. Real energy appears in equations. Real energy leaves traces. The steam engine did not ask for affirmations. It asked for fuel, pressure, and a working piston. And that is the kind of energy thermodynamics understands. Now, the fire inside an engine is not simply destruction. It is transformation. Chemical bonds in fuel are rearranged through combustion. Energy stored in molecular structures becomes thermal energy. Hot gases expand. Their pressure does work. But combustion also produces waste, gases, and heat that cannot all become useful work. The first law counts the energy. The second law limits the quality of conversion. This distinction matters because it prepares us for efficiency. An engine may obey the first law perfectly and still be inefficient. Energy is conserved even when most of it becomes waste heat. Conservation does not guarantee usefulness. This is a crucial idea. A car engine can waste much of the fuel's energy as heat. The energy is not destroyed, but it is no longer all available as useful motion. A light bulb may convert electrical energy into light and heat. An old incandescent bulb produces much heat compared with light. The energy is conserved, but the useful output may be small. The first law tells us the energy is still somewhere. The second law tells us why usefulness degrades. For tonight, we remain with the first law, the energy account, the ledger, the insistence that every machine, every fire, every engine, every breath must balance its transformations. But the engine also points us forward, because if thermodynamics began with heat engines, it soon reached living bodies. A body is not a steam engine. It has no boiler in the ordinary sense, no piston turning a crankshaft, no coal furnace under the ribs, thankfully. But a body is still a thermodynamic system. It takes in chemical energy. It transforms it. It does work. It produces heat. It maintains internal order. It exchanges energy and matter with the source. It must obey the same accounting. And that is where we go next. From fire and pistons to food and cells. From steam pressure to metabolism. From the engine room to the quiet machinery of the human body. Your body is not a steam engine. It does not have a boiler under the ribs. It does not burn coal in the chest. It does not turn a brass piston while you sleep. And yet, in a deep physical sense, your body is a thermodynamic system. It takes in energy. It transforms energy. It does work. It releases heat. It exchanges matter with its surroundings. It keeps an internal order that must be maintained every second. This is not metaphorical energy, not aura, not vibration, not a vague feeling of being inspired. This is real, biological energy. Chemical energy stored in food, oxygen taken in through the lungs, molecules broken down inside cells, ATP produced and used, muscles contracting, neurons firing, blood circulating, heat leaving through the skin. The first law of thermodynamics applies here too. Energy is not created by the body from nothing. The body must receive energy from physical sources, mostly food. Food contains chemical energy stored in molecular bonds, carbohydrates, fats, proteins. These molecules can be broken down and rearranged through metabolism. The energy released is captured, transferred, stored briefly, and used. The body does not simply have energy in the loose everyday sense. It processes energy. It manages a continuous budget. Every heartbeat has a cost. Every breath has a cost. Every thought has a cost. Every step has a cost. Even lying still has a cost. A sleeping body is not inactive. It is quietly busy. The heart continues to pump. The brain continues to organize activity. Cells repair. Ion gradients are maintained. Body temperature is regulated. Hormones shift. The immune system patrols. The lungs exchange gases. The liver processes molecules. The body is a night factory with the lights turned low. And every process requires energy. The main energy currency inside the cell is ATP, adenosine triphosphate. ATP is often described as the cell's energy currency because it can store and transfer usable chemical energy. When ATP is broken down into ADP and phosphate, energy becomes available for cellular work, muscle contraction, active transport across membranes, chemical synthesis, molecular motors, nerve signaling, maintenance of order. ATP is not mystical. It is not a spiritual fuel. It is a molecule involved in real chemical reactions. Your body produces and uses enormous amounts of ATP every day, not because ATP stays stored in huge piles, but because it is constantly recycled, made, used, remade, used again. A quiet molecular economy. Now, where does the energy for ATP come from? Much of it comes from the breakdown of glucose and fats. In the presence of oxygen, cells can extract energy efficiently through cellular respiration. Glucose and oxygen are transformed into carbon dioxide and water, while energy is captured in ATP and released as heat. This is not fire in the ordinary sense. Your cells are not tiny campfires. The process is controlled, stepwise, enzymatic, carefully regulated, but chemically, it is related to oxidation. Energy stored in molecules is transferred through a chain of reactions. The mitochondria play a central role. They are often called the powerhouses of the cell. Though the phrase is a little overused, still, it points to something real. Mitochondria help convert energy from food molecules into ATP through processes involving electron transport and proton gradients. Tiny differences in charge and concentration across membranes become part of the energy machinery of life. This is thermodynamics at microscopic scale, not vague vitality. Molecular physics, chemistry, energy gradients, membranes, enzymes, transport, heat, work. The body is full of gradients, concentration gradients, electrical gradients, temperature gradients, pressure differences. These gradients matter because they can drive processes. A nerve cell, for example, maintains differences in ion concentrations across its membrane. Sodium, potassium, calcium, chloride. Maintaining those gradients requires energy. When a neuron fires, ions move, electrical signals travel, information moves through the nervous system. Then energy is used again to restore the gradients. Even thought has thermodynamic roots, not because thoughts are only heat, not because consciousness is simple, but because the brain is a physical organ. It consumes oxygen and glucose. It produces heat. It relies on chemical and electrical processes. It obeys the first law. The brain cannot run on pure intention. It requires energy. This is one reason the body needs food, and oxygen, and rest. Now consider muscle movement. When you lift a cup, climb stairs, or even shift position in bed, muscles contract. Muscle fibers use ATP. Chemical energy becomes mechanical work. Some energy moves the body, some becomes heat. The muscles warm. The body may sweat to release excess heat. No biological process is perfectly efficient. The first law says the energy must be accounted for. The second law reminds us that some useful energy becomes dispersed as heat. But even before we reach the second law, the first law is already present. Food, energy, enters. Chemical transformations occur. Mechanical work is done. Heat is released. Internal energy changes. The books balance. Now, think of body temperature. The human body maintains a temperature within a narrow range. This requires thermodynamic regulation. If the environment is cold, the body loses heat faster. It may shiver. Shivering is muscle activity that produces heat. The body may constrict blood vessels near the skin to reduce heat loss. If the environment is hot, the body must release heat. Sweating allows evaporation to carry energy away. Blood flow to the skin may increase. Breathing and radiation also transfer energy. The body is constantly managing heat exchange with the surroundings. Again, this is not aura. It is not an energy field in the mystical sense. It is heat, transfer, conduction, convection, radiation, evaporation. A warm body in a cooler room transfers energy outward. A blanket does not create heat. It slows heat loss. It traps air. It reduces convection. It helps keep the body's own metabolic heat from escaping too quickly. That is thermodynamics under the covers. A small, soft laboratory of insulation. Now, think of calories. In everyday life, calories are often discussed in the context of diet. But physically, a calorie is a unit of energy. A food calorie, written with a capital C in nutrition contexts, is a kilocalorie. It represents the amount of energy needed to raise 1 kilogram of water by 1 degree Celsius. When food labels list calories, they are describing chemical energy available from food. The body does not always use all of it in the same way. Digestion, metabolism, absorption, and biological regulation are complex. But the basic idea is physical. Food contains energy. The body transforms it. Some becomes work. Some supports maintenance. Some is stored. Some leaves as heat. Some leaves in waste. The body's energy budget is real. That does not mean bodies are simple machines. They are not. Biology is complex, adaptive, and regulated. Hormones, enzymes, organs, microbiomes, nervous systems, behavior, sleep, stress, and environment all matter. But complexity does not exempt life from the first law. It makes the accounting more intricate, not optional. A living body is an open system. Matter enters and leaves. Food enters. Water enters. Oxygen enters. Carbon dioxide leaves. Water leaves. waste leaves, heat leaves. Work may be done on the environment. Because the body is open, its thermodynamics is more complex than a sealed gas cylinder, but the principle remains. Energy and matter crossing boundaries must be accounted for. This is why the phrase body energy can be misleading. In ordinary speech, someone may say they have low energy. Scientifically, this may connect to sleep, nutrition, hormones, illness, mental state, oxygen delivery, blood sugar regulation, stress, or many other factors, but it does not mean the person has lost some mystical, invisible substance. It means a complex biological system is not producing, distributing, or using usable energy in the usual way. The real explanation may be physiological, biochemical, neurological, psychological, environmental, often many at once. Real science does not make the body less mysterious. It makes the mystery more specific. Now let us follow a simple path. A piece of bread is eaten. Digestion breaks starch into glucose. Glucose enters the bloodstream. Cells take it up. Inside the cell, glucose is processed. Through glycolysis, the citric acid cycle, and oxidative phosphorylation, energy is transferred into ATP. ATP powers cellular work. Muscle fibers contract. The body moves. Heat is released. Carbon dioxide is exhaled. Water is formed. The energy originally stored in molecules has moved through the body's systems. Some has become motion. Some has become heat. Some may be stored for later as glycogen or fat. The energy has changed form. It has not appeared by belief, and it has not vanished by use. Now trace the chain backward. The bread came from grain. The grain came from a plant. The plant used sunlight, carbon dioxide, and water to build sugars through photosynthesis. Sunlight came from the sun. The sun's energy comes from nuclear fusion in its core. Hydrogen nuclei combine to form helium. A small amount of mass is converted into energy. That energy travels outward, eventually reaching Earth as light. Some of that light becomes plant chemistry. Some plant chemistry becomes food. Some food becomes ATP. Some ATP becomes muscle contraction. Some muscle contraction lifts your hand. A motion in your body can be traced back to sunlight, and deeper still, to nuclear reactions in a star. This is not poetic hand-waving. It is the physical ancestry of energy. The first law lets us follow the family tree. Energy does not need to be vague to feel profound. It becomes more profound when we can trace it. Now consider sleep. Sleep may seem like a time of stillness, but a sleeping body continues to use energy. The brain remains active. Different sleep stages have different patterns. Cells continue maintenance. Protein synthesis occurs. Waste products are cleared. Body temperature changes. Breathing continues. The heart beats. The immune system communicates. Dreams may arise. The body is not turned off. It is reorganizing, repairing, balancing. A sleeping body is a thermodynamic system in a quieter mode. Energy use continues, but the pattern changes. That is a gentle thought for a channel like ours. Even in rest, physics remains. Even in sleep, metabolism keeps the books. Even in stillness, molecules move. This does not make rest mechanical, in a cold way. It makes rest part of nature's quiet order. The warmth under a blanket is not fake energy. It is real heat, produced by metabolism and slowed by insulation. The slow breath is not symbolic energy. It is gas exchange. Oxygen entering, carbon dioxide leaving. The heartbeat is not just metaphorical life force. It is muscular work, electrical signaling, pressure, flow, chemistry, and energy transformation. The body is not less alive because we describe it scientifically. It becomes more astonishing. Now, there is one more important point. The first law says energy is conserved, but the body must keep taking in energy because energy is constantly leaving. Heat leaves through the skin. Work is done on the environment. Chemical energy is used and transformed. Matter leaves in waste products. If no energy enters, the body must use stored energy, glycogen, fat, eventually other tissues in extreme conditions. The body survives by managing reserves. There is no biological loophole. No organism lives by creating energy from nothing. Life is open to its environment. It survives by taking in energy and matter, using them to maintain structure, and releasing energy and matter back out. Life is a pattern maintained by flow. That phrase is worth holding softly. Life is a pattern maintained by flow, not by violating thermodynamics, by using thermodynamics. Plants capture sunlight. Animals eat plants or other animals. Microbes process chemical gradients. Deep-sea ecosystems may use chemical energy from hydrothermal vents. Every living system must have an energy source. Different sources. Same law, input, transformation, output, maintenance. The first law is present in every cell. Now return to the message of this video. Energy is not a vague magic word. It is not merely motivation. It is not a mood in the room. In the body, energy means chemical bonds, ATP, ion gradients, muscle work, heat transfer, metabolism, and measurable exchange with the source. When someone says, protect your energy, they may mean protect your attention, boundaries, mood, or emotional health. That can be meaningful in everyday life, but it is not the same as thermodynamic energy. The scientific word energy should not be stretched until it loses its bones. It has bones, joules, calories, molecules, gradients, heat, work, internal energy. The body reminds us why precision matters, because real energy is already intimate. It is in the warmth of your hands, the breath in your lungs, the glucose in your blood, the ATP in your cells, the heat under your blanket, the motion of your heartbeat, the sunlight hidden in food. You do not need to turn energy into myth to make it personal. It is already personal. It is keeping you alive right now, quietly, chemically, thermodynamically, and as the body exchanges energy with its surroundings. Earth itself is doing something similar, on a much larger scale. Our planet receives sunlight, reflects some of it, absorbs some of it, radiates heat back into space, moves energy through oceans, winds, clouds, storms, and climate. The same accounting that applies to a sleeping body also applies to the atmosphere above it. So next, we will lift our view from cells to skies, from metabolism to weather, from body heat to sunlight, and from the quiet thermodynamics of life to the vast energy flow of Earth. Farasai, Lanmeitian. Earth is also a thermodynamic system, not a simple one, not sealed like a glass jar, not quiet like gas in a textbook cylinder. Earth is open to space. It receives energy from the sun. It radiates energy back into the darkness. It moves energy through oceans, winds, clouds, ice, land, storms, and living things. It is a planet of flows, a blue thermodynamic machine turning slowly in sunlight. The first law applies here too. Energy cannot be created from nothing. Weather does not come from nowhere. Wind does not blow without a source. Clouds do not form without energy transfers. Rain does not fall outside physics. The atmosphere is not random theater above our heads. It is motion, heat, water, pressure, gravity, radiation, and conservation, all moving together. The main energy source for Earth's weather is sunlight. Sunlight reaches the top of the atmosphere as electromagnetic radiation. Some of it is reflected back into space by clouds, ice, aerosols, and bright surfaces. Some is absorbed by the atmosphere. Some reaches the land and oceans. The absorbed sunlight warms Earth's surface. The surface then transfers energy to the air above it through radiation, conduction, convection, evaporation, and from there, the energy begins to travel. The planet does not heat evenly. The equator receives more direct sunlight than the poles. Day and night alternate. Land warms and cools faster than ocean. Clouds reflect sunlight in some places. Dark surfaces absorb more. Ice reflects more. Mountains disturb air currents. Oceans store enormous amounts of heat. This uneven heating creates differences, temperature differences, pressure differences, density differences, and differences are where motion begins. Warm air tends to expand and become less dense. Cool air tends to be denser. Pressure gradients form. Air begins to move. That movement is wind. Wind is not mysterious energy. It is air in motion, driven by pressure differences that ultimately come from uneven heating. The sun warms Earth unevenly. The atmosphere responds. Air flows. The rotating earth bends that flow through the Coriolis effect. Mountains, oceans, land, and seasons shape it further. A breeze at night, a trade wind over the ocean, a jet stream high above, a storm system turning across a continent. All are parts of Earth's energy accounting. Energy enters from sunlight. Energy moves through the atmosphere. Energy becomes motion. Energy becomes heat. Energy becomes phase changes in water. Energy leaves again as infrared radiation. The books must balance, but the pages are enormous. Now consider the ocean. The ocean is one of Earth's great heat reservoirs. Water has a high heat capacity. That means it can absorb a large amount of energy while changing temperature relatively slowly. This is why coastal regions often have milder temperatures than inland regions. The ocean stores heat, moves heat, releases heat. Currents carry warm water from one region to another. Cold water rises in some places. Warm surface water evaporates. The ocean and atmosphere speak constantly through energy exchange. A warm ocean surface can transfer energy to the air. Water evaporates. Evaporation requires energy. Molecules at the surface escape into the air as water vapor. That energy becomes hidden in the vapor as latent heat. Latent heat is energy associated with a phase change. When liquid water becomes vapor, energy is absorbed. When vapor condenses back into liquid droplets, energy is released. This is one of the great engines of weather. A cloud is not just white decoration. It is part of a thermodynamic process. Water evaporates from ocean, lakes, soil, and plants. Water vapor rises and cools. As air cools, it may reach saturation. Water vapor condenses into tiny droplets or ice crystals. Clouds form. During condensation, latent heat is released into the air. That released energy can help air rise further. It can strengthen storms. It can shape convection. It can feed towering clouds. A thunderstorm is not powered by mood. It is powered by heat, moisture, uplift, condensation, and energy transfer. Again, no vague energy needed. The real physics is already dramatic enough, even when told softly. Now, think of a rainstorm. Sunlight warmed the ocean. Some of that energy evaporated water. Water vapor entered the air. Air moved, lifted, cooled, condensed. Cloud droplets grew. Rain fell. The falling rain carried mass and energy downward. The atmosphere changed. The surface changed. The cycle continued. The water cycle is also an energy cycle. Evaporation stores energy. Condensation releases energy. Winds transport vapor. Clouds reflect sunlight. Rain cools surfaces. Snow stores water and reflects light. Ice changes Earth's energy balance. The familiar story of rain is quietly thermodynamic. The first law follows the energy through every step. Now consider Earth radiating heat into space. Earth receives sunlight mainly as visible and near-visible radiation. After absorbing energy, Earth emits infrared radiation. This is heat energy leaving the planet. For Earth's temperature to remain roughly stable over long periods, incoming energy and outgoing energy must be in balance. If more energy enters than leaves, Earth warms. If more energy leaves than enters, Earth cools. This is planetary energy accounting. The first law does not decide the exact temperature by itself, but it tells us that energy imbalance must produce change somewhere. In the oceans, atmosphere, iceland, biosphere, or outgoing radiation. The climate system is complex, but it is not free from bookkeeping. Greenhouse gases matter because they affect how infrared radiation moves through the atmosphere. They do not create energy. They change the rate and pathway by which energy leaves Earth. Certain gases absorb and emit infrared radiation. This makes the atmosphere more effective at retaining heat near the surface than it would be otherwise. The greenhouse effect is not a myth. It is radiative physics. Without a natural greenhouse effect, Earth would be much colder. With changes in greenhouse gas concentrations, the energy balance changes. Again, the point is accounting. Sunlight in, reflection out, absorption, heat storage, infrared radiation out, atmospheric interaction. The law does not take sides, it counts. This is why climate science is not based on vague feelings about the planet. It is based on measurements, radiation, temperature, ocean heat content, atmospheric composition, ice mass, energy flows, satellite observations, thermodynamics, fluid dynamics, chemistry, earth science. The atmosphere may look soft from below. Clouds drifting, winds moving, rain falling. But underneath the softness is accounting. Energy enters, energy moves, energy changes form, energy leaves. Now, the weather you feel on your skin is local. A warm afternoon, a cold wind, a humid night, a foggy morning. But each local feeling is connected to larger flows. A breeze at the coast can come from different heating rates between land and sea. During the day, land warms faster than water. Air over land warms and rises. Cooler air from the sea moves in. A sea breeze forms. At night, the pattern can reverse. The land cools faster. Air flows differently. A simple daily wind can be explained through heat capacity, pressure, and energy transfer. No mystical force, no atmospheric mood, just the planet adjusting its account. Mountains also shape energy flow. Air forced upward, over a mountain expands and cools. If it cools enough, water vapor condenses. Clouds and precipitation may form on one side. As air descends on the other side, it compresses and warms. Dry regions can appear in rain shadows. Again, thermodynamics becomes landscape. A mountain does not only stand there, it edits the movement of air and energy. The same physical principles create soft fog in a valley, snow on high peaks, and dry winds on the far side of a range. Now consider hurricanes. We do not need to make the scene frightening. We can describe the physics calmly. A hurricane draws energy from warm ocean water. Evaporation supplies moisture. Condensation releases latent heat. Rising air lowers pressure. Surrounding air flows inward. Earth's rotation helps organize the circulation. The storm becomes a heat engine of the atmosphere. It takes energy from the warm ocean and moves it through wind, clouds, rain, and heat release. The first law accounts for the energy. The second law helps describe why heat engines need temperature differences and why not all heat becomes useful work. But for our purposes, the key point is this. Even the most powerful storms are not outside thermodynamics. They are thermodynamics made visible, swirling, moist, large, dangerous sometimes, but physical. A storm is a moving account of heat, work, water, and air. Now think of ice. Ice reflects much more sunlight than dark ocean water. So when ice covers a region, more sunlight is reflected back into space. Less energy is absorbed by the surface. When ice melts, darker water or land may be exposed. More sunlight can be absorbed. This changes the energy balance. Ice also stores energy in phase changes. Melting requires energy. Freezing releases energy. A glacier, a snowfield, a frozen lake, and a polar sea are not just scenery, they are thermodynamic participants. They store, reflect, absorb, and exchange energy. The first law is there too. In every melting snowflake, in every freezing drop, in every slow change of a polar landscape. Now think of the daily cycle. Morning sunlight touches the ground. The surface warms. Air above it warms. Convection begins. Clouds may build. In the evening, sunlight fades. The surface radiates heat. Air near the ground cools. Dew may form. Fog may appear. The night becomes a slow exchange of energy between ground, air, water, vapor, and space. A quiet thermodynamic lullaby. The same law that describes a piston also describes the cooling of a field under starlight. This is the beauty of thermodynamics. It scales from gas in a cylinder to cells in a body, 2 winds over an ocean, to radiation leaving Earth. The details change. The accounting remains. Now, Earth is not an isolated system with respect to energy. It receives sunlight and emits radiation. But for matter, Earth is nearly closed on human timescales. Aside from small amounts entering and leaving through space dust, atmospheric escape, and human spacecraft. This means energy flows strongly through the system, while matter mostly cycles within it. Water cycles, carbon cycles, nitrogen cycles, heat flows. Radiation enters and leaves. Life operates inside these flows. Plants capture sunlight. Animals use chemical energy. Microbes transform molecules. Forests exchange water and energy with the air. Oceans store and release heat. Clouds regulate light and radiation. The biosphere is tangled with the climate system, and the climate system is tangled with thermodynamics. There is no separate Earth energy in the mystical sense. There is solar radiation, thermal radiation, latent heat, sensible heat, kinetic energy of winds and currents, chemical energy in living systems, gravitational potential energy in water, lifted by evaporation and later falling as rain. These are real forms and transfers, measured, modeled, studied, debated with data. The planet does not run on vibes, it runs on physics. And still, it is magnificent. Perhaps more magnificent, because every cloud has a history, every breeze has a source, every raindrop has traveled through energy transformations, every warm stone at sunset contains a small memory of sunlight, every gust of wind is the atmosphere trying to smooth differences created by uneven heating. Earth is not less poetic when understood scientifically. It becomes poetry with instruments, a poem written in joules, pressure, radiation, and water vapor. Now, let us return to the first law. For any part of Earth we choose, as a system, we can ask the same questions. How much energy enters? How much leaves? How much is stored? How much becomes motion? How much becomes heat? How much is carried by a water-changing phase? How much is transported by wind or ocean current? A patch of ocean? A cloud? A forest? A desert? An air mass? A storm? A continent? The questions remain. The answers may be complicated, but the law is steady. Energy is conserved. Changes must be paid for. Flows must have sources. Losses must go somewhere. The weather is not random in the sense of lawless. It is complex, sensitive, chaotic. Difficult to predict in detail far ahead, but not lawless. Weather obeys physics. Even chaos has equations. A cloud may look soft, but it is built on thermodynamics. A wind may feel invisible, but it carries kinetic energy. A warm night may feel still, but radiation is leaving the ground and atmosphere. A storm may seem wild, but it is shaped by energy gradients. The wildness is lawful. That is a lovely contradiction. A storm can be both unpredictable in detail and obedient to physics. A cloud can be both delicate and thermodynamic. A breeze can be both gentle and part of planetary energy transport. The first law helps us hold both ideas at once. Wonder and accounting, softness and structure, weather and energy. And as we lift our view even higher, beyond Earth's clouds and oceans, the same principle continues. The sunlight driving our weather comes from a star. The sun itself is a vast energy transformation. Deep in its core, nuclear processes release energy. That energy travels outward through plasma, radiation, and convection. Eventually, some of it reaches Earth. Some warms oceans. Some grows forests. Some becomes wind. Some becomes food. Some becomes the warmth of a sleeping body. So the next step is natural. From Earth's atmosphere to the stars. From weather to sunlight. From planetary energy flow to cosmic energy transformation. And from the quiet accounting of Earth to the shining engine at the center of our days. The energy that moves through Earth does not begin on Earth. Much of it begins in a star. Our star, the sun. Every breeze over an ocean. Every cloud built from evaporation. Every green leaf storing chemical energy. Every warm stone at sunset. Every meal that traces back to plants. Every breath supported by photosynthesis. Every soft patch of daylight on a floor. All of it is connected to energy transformations in the sun. The sun is not a mystical lamp. It is not a symbol, doing physics by metaphor. It is a star. A vast sphere of hot plasma, held together by gravity. Deep inside it, pressure and temperature are enormous. Hydrogen nuclei move at tremendous speeds, and under those extreme conditions, nuclear fusion can occur. Fusion is the process in which light atomic nuclei combine to form heavier nuclei. In the sun, the main process converts hydrogen into helium through a chain of nuclear reactions. The details are complex, but the central idea is this: some mass is converted into energy. That energy is released according to Einstein's famous relation between mass and energy. E equals mc squared. The amount of mass converted in each reaction is tiny, but the sun contains an enormous amount of matter, and the reactions occur in vast numbers. So the total energy release is immense. This is not energy from nothing. The sun is not violating the first law. Mass itself is a form of energy. Nuclear fusion transforms the energy stored in mass and nuclear binding arrangements into radiation, particle motion, and heat. The account still matters. Nothing is being created for free. The sun shines because matter and energy are deeply connected. This is one of the great expansions of the conservation idea. In everyday thermodynamics, we often track heat, work, and internal energy. In nuclear physics and relativity, mass energy enters the story. The accounting becomes deeper. But it does not become mystical. It becomes more precise. The sun's core is the furnace, but not a furnace like one built of metal. It is a plasma. Electrons are separated from nuclei. Particles move in a hot, dense sea. Gravity compresses the star inward. Pressure pushes outward. The sun remains stable because these effects balance. Gravity tries to crush the sun. Internal pressure from hot plasma and radiation resists collapse. This balance is called hydrostatic equilibrium. A quiet balance, even inside a roaring star. The sun is not exploding apart, and it is not collapsing inward. It is holding itself in a long, luminous negotiation between gravity and pressure. Fusion in the core supplies the energy that helps maintain that pressure. Energy released in the core begins a long journey outward. This journey is not simple. A photon produced in the core does not usually fly straight out into space in a clean line. Inside the sun, matter is dense. Photons are absorbed and re-emitted many times. Energy moves through the radiative zone slowly, scattered through the plasma. Farther outward, convection becomes important. Hot plasma rises, cooler plasma sinks. Energy is carried by large-scale motion. Eventually, energy reaches the surface region, the photosphere. From there, light can escape into space. The sunlight that touches Earth has a history. It began as energy from nuclear fusion. It moved through the interior of a star. It emerged as electromagnetic radiation. Then it crossed about 150 million kilometers of space. After roughly 8 minutes of travel, some of that light reached Earth, a small part of the sun's output, tiny compared with the total energy it radiates, but enough to shape the atmosphere, oceans, climate, and biosphere of a planet. This is the scale of energy transformation: cold fusion, radiation transport, solar light, planetary heating, weather, photosynthesis, food, metabolism, heat, motion, life. The first law lets us trace the chain. It does not make the chain dull. It makes the chain intelligible. Now think of a plant leaf. Sunlight arrives. Molecules in the leaf absorb certain wavelengths. Photosynthesis uses light energy to help convert carbon dioxide and water into sugars and other molecules. Oxygen is released. Chemical energy becomes stored in molecular bonds. Later, that stored energy may be used by the plant, or eaten by an animal, or decomposed by microbes, or buried over long times and transformed into fossil fuels under geological conditions. When we burn fossil fuels, we are releasing ancient sunlight stored in chemical form. Coal, Oil and gas are not magic rocks. They are part of long energy histories. Sunlight captured by life, buried, compressed, transformed, then burned by humans to release stored chemical energy. The flame in a furnace is connected to the sun through deep time. Again, no vague energy needed. The story is already astonishing. Now consider your body again. If you eat bread, rice, fruit, or vegetables, the chemical energy in that food was assembled by plants using sunlight. If you eat meat, the animal obtained energy by eating plants or other organisms that ultimately trace back through food webs. Your body breaks down molecules and uses the released energy to make ATP. ATP powers cells. Muscles move, heat is produced. Breath continues. The warmth of your body is, in a long chain, connected to the sun. A human heartbeat is not powered by cosmic metaphor. It is powered by chemical energy that can be traced through biology, chemistry, and astrophysics. That is more intimate than myth, more precise, and somehow more gentle. Now think of wind. Sunlight heats earth unevenly. Air pressure differences form. Air moves. Wind carries kinetic energy. A wind turbine can extract some of that kinetic energy and convert it into electrical energy. The electricity may power a lamp. That lamp emits light and heat. A person reads under it. The room warms slightly. The source, once again, is sunlight. Solar energy became atmospheric motion. Atmospheric motion became turbine rotation. Rotation became electricity. Electricity became light and heat. The first law does not say the forms stay the same. It says the accounting follows them. Now think of hydroelectric power. Sunlight warms oceans and lakes. Water evaporates. Water vapor rises. Clouds form. Rain or snow falls at higher elevations. Water stored high above sea level has gravitational potential energy. When it flows downward through a dam, that potential energy becomes kinetic energy. Turbines turn. Electricity is generated. The source is not simply the river. The source is the water cycle, driven largely by solar energy, working with gravity. Sunlight lifts water, gravity brings it down. A turbine sits in a conversation between the two. Now think of solar panels. They do not create energy from nothing. They convert electromagnetic energy from sunlight into electrical energy. A photovoltaic cell uses the properties of semiconductor materials. Photons from the sun interact with electrons in the material. Electrical current can be generated. Some energy becomes electricity, some becomes heat. The accounting still balances. A solar panel is not a free energy machine in the impossible sense. It has an input, sunlight. It has outputs, electricity, heat, reflected light, material losses, a real device obeying real physics. This is why the sun is such a powerful example for our topic. It shows that enormous energy flows can be real without being mystical. The sun gives Earth energy, but not as spiritual permission, as radiation, photons, electromagnetic waves, physical energy traveling through space. The fact that this radiation allows weather, food, forests, and warmth is magnificent, but it is magnificent because it is real. Now, stars are not all the same. Different stars have different masses, temperatures, colors, lifetimes, and fusion processes. Massive stars burn through nuclear fuel more quickly and can end their lives dramatically. Smaller stars can shine steadily for far longer. Some stars become red giants. Some leave behind white dwarfs. Some massive stars explode as supernova. Some collapse into neutron stars or black holes. In each case, energy transformations govern the story. Gravity, fusion, radiation, thermal pressure, nuclear binding energy, mass energy, conversion, neutrinos, shock waves, stellar winds. The universe is not static. It is full of transformations, and through those transformations, energy is tracked. In ordinary stars like the sun, fusion builds helium from hydrogen. In massive stars, later stages can build heavier elements, carbon, oxygen, neon, silicon, iron. The creation and dispersal of elements through stellar evolution and supernova helped make planets, rocks, oceans, and life possible. The atoms in your body were forged through cosmic processes. But again, this is not mystical energy language. It is nuclear physics and astrophysics. It is matter changing form under extreme conditions. It is energy moving through stars and space. The poetry is real because the physics is real. Now let us be careful. When we say stars transform mass into energy, we are not saying energy appears from absolute nothing. Mass and energy are related. A decrease in mass energy in one form appears as energy in other forms. The total accounting remains deeper than our everyday categories. This is why conservation laws had to grow with modern physics. Classical mechanics taught conservation of mechanical energy in ideal systems. Thermodynamics unified heat and work. Electromagnetism showed energy in fields and radiation. Relativity connected mass and energy. Quantum physics revealed discrete energy levels, photons, and nuclear processes. The idea of energy became broader, not looser, more exact, not vaguer. This is another important lesson. Real science can expand a concept without turning it into fog. Energy in physics grew from mechanics to heat, from heat to fields, from fields to mass energy, from chemistry to nuclei. At each step, it gained equations, units, measurements, predictions, and tests. It did not become a blank word for whatever someone wants to believe. The scientific concept of energy became larger because it became more disciplined. That is the opposite of superstition. Now consider the night sky. When you see stars, you are seeing energy traveling across space. Some of that light has traveled for years, some for hundreds of years, some for thousands, some from galaxies, millions or billions of light years away. The light carries information, temperature, composition, motion, distance. Astronomers use spectra to study stars. By splitting light into wavelengths, they can identify elements, temperatures, velocities, magnetic fields, and more. Light is not just brightness. It is a messenger of energy and structure. A star does not need to be visited to be studied. Its radiation carries a record. In this way, energy traveling through space becomes knowledge. Photons leave a star. They cross the universe. They enter a telescope. They strike a detector. They become data. And from that data, we learn about the physical conditions of distant worlds. Again, no mysticism is required. The cosmos is already generous with evidence. Now, how does this connect back to the first law? Every star has an energy budget. Energy is generated or transformed in the core. Energy is transported outward. Energy is radiated into space. The star's structure adjusts to balance gravity, pressure, and energy flow. If fusion changes, the star changes. If fuel runs low, the star evolves. A star's life is an energy story, not a mood, not a symbol, a physical history written in mass, heat, pressure, radiation, and gravity. The sun's energy budget is what makes Earth's energy budget possible. Earth receives only a tiny fraction of the sun's radiation, but that fraction drives most surface life and weather. The first law helps us follow the path. Sun to earth, light to heat, heat to wind, light to chemistry, chemistry to metabolism, metabolism to motion and warmth, motion and warmth to the surroundings. Eventually, energy radiates away into space. This is not a circle that returns perfectly to where it began. Energy changes form and spreads. Again, usefulness and direction belong more deeply to the second law, but the first law gives us the continuity, the thread, the assurance that each transformation has a source. When sunlight warms your face, that energy was not created in your skin, it arrived. When your skin warms the air, energy leaves you. When you move your hand, chemical energy becomes mechanical work and heat. When a plant grows, light energy becomes chemical structure. When a star shines, nuclear mass energy becomes radiation. Each step belongs to the same universe of accounting. This is why thermodynamics feels both humble and cosmic. It begins with a piston in a workshop. It reaches a body under a blanket. It rises through clouds. It arrives at the core of a star. The same idea travels. Energy changes form. Energy crosses boundaries. Energy is conserved. The setting changes from brass to blood to blue atmosphere to plasma, but the ledger follows. Now, there are deep subtleties in cosmology. On the scale of the entire expanding universe, defining total energy can be complicated. General relativity treats space-time itself as dynamic. Light can be redshifted by cosmic expansion. The global energy account is not always simple, in the same way as for a gas in a box. This is worth mentioning because real science does not fear nuance. But for stars, planets, machines, bodies, and thermodynamic systems, energy conservation remains an extraordinarily powerful guide. It has earned that trust through measurement, through prediction, through engineering, through astronomy, through the stubborn agreement of nature. The sun rises, the atmosphere moves, plants grow, bodies warm, engines turn, stars shine, and everywhere, energy has a path. That path may be long, it may be hidden. But for stars, planets, machines, bodies, and thermodynamic systems, energy conservation remains an extraordinarily powerful guide. It has earned that trust through measurement, through prediction, through engineering, through astronomy, through the stubborn agreement of nature. The sun rises, the atmosphere moves, plants grow, bodies warm, engines turn, stars shine, and everywhere, energy has a path. That path may be long, it may be hidden. All of them belong to one story of transformation. The story is not simple, but the rule is steady. Energy cannot be created from nothing. energy cannot be destroyed into nothing. It can become heat, work, light, motion, chemical structure, radiation, internal energy, mass energy, and onward. The universe changes by transforming what it already has. That is not a small idea. It is a midnight-sized idea, large enough to hold engines, bodies, weather, and stars in the same quiet hand. And now, we are nearly ready to close the journey. We began by rescuing the word energy from fog. We followed it through physics, heat and work, pistons and steam, food and cells, earth and weather, stars and light. And in the final scene, we will return to the simple image beneath it all, a ledger, a quiet ledger of the universe, where every transformation has an entry, and every real change leaves a trace. And now, we can let the ledger close for tonight, not because the story of energy is finished, but because we have followed it far enough to see its shape. We began with a word that is everywhere. Energy. A word used in science, in daily life, in health, in emotion, in advertising, in vague promises, in soft language, in strange claims, and we slowed it down. We took away the fog. We took away the costume. We took away the idea that energy is simply a mood, a vibration, an aura, or a secret force that obeys intention. In physics, energy is not a vibe. It is not a mystical glow. It is not something created by wanting. It is a measurable physical quantity. It can be stored, transferred, transformed, calculated, tracked. It can appear as motion, heat, light, chemical structure, electrical potential, nuclear binding, gravitational position, radiation, internal energy. But it does not appear from nowhere, and it does not vanish into nothing. That is the heart of the first law of thermodynamics. Energy changes form. Energy crosses boundaries. Energy moves from system to surroundings, and from surroundings to system. But the account must balance. The first law is not flashy. It does not shout. It does not decorate itself with mystery. It simply says that when a system changes, energy is part of the story. If heat enters, the system's internal energy may rise. If the system does work, energy leaves. If work is done on the system, energy can enter. If heat flows out, energy is carried away. The details may vary. The signs in the equation may depend on convention, but the physical message remains steady. No free creation, no silent disappearance, no cosmic loophole in the books. We saw that heat is not a substance hidden inside objects. Heat is energy in transit, energy crossing a boundary because of temperature difference. A hot cup warms a cooler room. A flame warms a kettle. A warm body loses energy to cold air. Heat moves because physical systems interact, and once the energy has crossed the boundary, it belongs to the internal energy of something else, or continues onward in another form. We saw that work is another way energy crosses boundaries. A gas expands and pushes a piston. A hand lifts a weight. A motor turns a shaft. A compressor squeezes air. A battery drives current through a circuit. Work is organized. Energy transfer, force, motion, pressure, expansion, compression, electrical flow, mechanical action. It is not abstract inspiration. It is physical change. We saw that internal energy is the energy stored within a system at the microscopic level. Molecules moving, atoms vibrating, particles interacting, bonds storing energy. Matter, holding energy in ways too small for the eye, but not too small for physics. A cup of tea may look still, but inside it, molecules are restless. A gas may look invisible, but inside it, particles collide and carry energy. A body may appear asleep, but inside it, cells are working quietly through the night. The world is never as still as it looks. Then, we open the law itself. Delta U,等于Q减 W. A small equation, almost too small for what it contains. The change in internal energy equals the heat added to the system minus the work done by the system. In that equation, engines begin to make sense. Pistons begin to make sense. Cooling cups, warm blankets, power plants, batteries, muscles, clouds, stars, all become entries in the same physical account. The first law is a ledger, and the ledger is patient. It does not care about slogans. It does not care about wishful machines. It does not care about dramatic claims. It asks only what entered, what left, what changed, and where the energy went. We looked at the old dream of free energy, a machine that powers itself, a wheel that turns forever, a device that gives more than it receives. And we saw why the first law refuses it. Not because science lacks imagination, but because imagination must still pay the account. A motor that turns has an input. A lamp that glows has a source. A battery that powers a circuit is being drained. A wheel that spins slowly loses energy to friction, heat, vibration, and sound. Low loss is not free creation. Persistence is not production. A machine may be clever, it may be efficient, it may be beautiful, but if it produces work, the energy must come from somewhere. The books include the small print. Then we went back to the birth of thermodynamics. To fire, steam, pressure, pistons, engines. The laws did not appear from a cloud of philosophy. They came from practical questions. How does heat become motion? How much work can a steam engine produce? Why is fuel consumed? Why do machines waste heat? Why do engines need a continuous source? Thermodynamics was born in workshops, mines, boilers, and measurements. The universe sometimes reveals itself in soot, and from those smoky machines came clean laws. Heat and work were seen as connected. Mechanical action could warm water, heat could expand gas and move pistons, energy could transform. The first law became the grammar of that transformation. Then we moved from engines to the body. A body is not a steam engine, but it is a thermodynamic system. It takes in food and oxygen. It transforms chemical energy. It produces ATP. It does cellular work. It moves muscles. It fires neurons. It pumps blood. It releases heat. Even in sleep, the body keeps its account. The heart beats, the lungs exchange gases, cells repair, the brain remains active. The body is not turned off at night. It is quietly reorganizing, quietly maintaining order, quietly spending and transforming energy. This is not mystical life force. It is biology, chemistry, thermodynamics, and it is more intimate than myth. The warmth under a blanket, the breath in the lungs, the glucose in the blood, the ATP in the cells, the sunlight hidden in food. Real energy does not need to be vague to be personal. It is personal already. It is keeping us alive. Then we lifted our view to Earth, a planet of flows. Sunlight enters. Some is reflected, some is absorbed. Oceans store heat. Air moves, water evaporates. Clouds form, rain falls. Winds blow, ice reflects light. Earth radiates infrared energy back into space. Weather does not come from nowhere. The atmosphere is not random theater. It is heat, motion, pressure, water, gravity, rotation, and radiation moving together. The water cycle is also an energy cycle. Evaporation stores energy. Condensation releases it. Storms are powered by heat, moisture, uplift, and phase change. The planet does not run on vibes. It runs on physics. And because it runs on physics, we can study it, measure it, model it, argue about it with data, understand it more deeply. Finally, we followed energy back to the stars. The sunlight that warms Earth begins in the sun, a real star, a vast sphere of hot plasma held together by gravity. Deep in its core, nuclear fusion transforms hydrogen into helium. Some mass energy is released as radiation and heat. That energy travels outward through the sun, escapes into space, crosses the distance to Earth, warms oceans, feeds weather, grows plants, becomes food, moves through bodies, leaves again as heat. The chain is enormous, but it is not mystical. It is physical. The sun is not a magical lamp. It is a star, and stars are energy transformations written across cosmic time. This is the quiet grandeur of the first law. It connects the small and the vast. A piston in a workshop, a candle on a desk, a sleeping body, a cloud over the ocean, a forest leaf, a turbine, a cup of tea, a star. Different scenes, different scales, one deep accounting. Energy changes form. Energy crosses boundaries. Energy is conserved. The universe changes by transforming what it already has. That may sound strict, but it is not cold. It is beautiful, because it means the world is connected by lawful change. A flame has a source, a wind has a source, a heartbeat has a source, a star has a source, a machine has an input, a body has metabolism, a storm has heat and moisture, a light has radiation. Every real change leaves a trace. Every transformation has an entry. Every process asks to be understood. That is why real science is stronger than the fog. The fog says energy can mean anything. Science says energy means something. Something measured. Something tested. Something conserved. Something that builds engines, explains weather, powers cells, and lets stars shine. The vague version of energy may sound easy, but the real version is larger. It has units, equations, experiments, history, technology, biology, planetary systems, cosmic light. It does not become smaller when we make it precise. It becomes deeper. So when someone says energy is everything, we can answer gently. Energy is not everything, but energy is involved in every physical change. That difference matters. Energy is not a mood, but moods have biological processes that require energy. Energy is not a spiritual glow, but bodies glow faintly with thermal radiation. Energy is not intention, but intention depends on a brain that consumes chemical energy. Energy is not magic, but it is one of the most powerful ideas in science. The first law helps protect that idea. It keeps the word from dissolving into mist. It gives energy, its bones, heat, work, internal energy, systems, boundaries, transfers, transformations, conservation, a quiet framework, a serious framework, a framework strong enough to hold engines, bodies, weather, and stars. And perhaps that is the best place to end. Not with a machine that runs forever. Not with a mystical field. Not with a slogan, but with a simple account. A cup cools beside the window. The warmth moves into the room. A body rests under a blanket. Cells continue their quiet chemistry. Clouds drift above the sleeping city. Winds carry energy across the dock. Far away, the sun will rise again. Not because energy is being created from nothing, but because a star is still transforming mass energy into light. And that light will begin another day of motion, warmth, weather, food, work, and life. The ledger continues. Softly, strictly, beautifully. Thank you for spending this calm journey with Midnight Science. If you are still awake, you can let the final thoughts stay for a moment. The universe does not give something for nothing, but it gives us transformation. Fire into steam, food into motion, sunlight into wind, stars into warmth, energy into change.